So let me share my screen. So can you see my screen now? So that's good. So I would like to start by thanking the organizers for organizing this seminar series and for giving me an opportunity to give a talk. So thank you very much. So I will start by defining the basic object that we're going to be discussing today, which are knots. So what is a knot? A knot is an embedded of the circle S1 into the 3 sphere. So here we have some example knots. In knot theory, we say that 2 knots are equivalent if there is an ambient isotopy between them in S3. In other words, one knot is equivalent to the other if one can be deformed to the other without carrying them. The main goal of knot theory is to say when 2 knots are equivalent or not. And to answer this question, many theories have been developed. In particular, there is one called the Hyperbolic Knot theory. Hyperbolic Knot theory aims to study hyperbolic knots. So what is a hyperbolic knot? A knot is hyperbolic if its complement in S3 admits a complete metric with all sectional curvatures equal to -1. So we see that this definition of hyperbolic knot is very geometric. However, Thurston proved that a non-trivial knot is hyperbolic if and only if its complement in S3 doesn't have an essential tori and any line. Therefore, the first definition of hyperbolic knot was very geometric. However, it ended up being very topological, because now, if we want to prove that a knot is hyperbolic, we just need to study certain type of surfaces in its complement in S3. More precisely, tori and any line. So we define a satellite knot as a knot whose complement has an essential torus. Here, we have an example of a satellite knot. The knot that is wrapping around the core of the torus is a satellite knot. Soon, I'm going to tell you more precisely what is an essential torus. But before that, let me tell you what is a torus knot. A torus knot is a knot that whose complement has an essential endless but does not have an essential torus. Here, we have an example of a torus knot. The blue knot is a torus knot because torus knot can also be defined as knot that can be embedded on the trivial torus. So we see that this knot here, the blue knot, is embedded on the trivial torus. Therefore, a non-trivial knot is either a torus knot, a satellite knot, or has hyperbolic complement. Therefore, if we want to apply hyperbolic knot theory to study a knot, the first thing that we need to know if this knot is hyperbolic or not. And to answer this question, we just discovered that we just need to study certain type of surfaces in its complement in S3, more precisely essential tori and essential any line. So that's why essential tori and essential any line are very important. Today, I'm going to talk about essential tori in the complement of twisted torus knots. But before defining twisted torus knots, let me tell you what is an essential torus. We start here with this definition of incompressible torus. So a torus is incompressible if we consider a disk with boundary in this torus, then the boundary of this disk bounds a disk in the stories. So let me start here with one example that is compressible, so not incompressible. So let's consider here the trivial torus. The trivial torus is defined as a torus whose core is the trivial knot. The trivial knot is this knot here. So we see that the core of this torus here is this knot. So let's consider now a disk with boundary in the longitude of the torus, this disk here. We see that the bound of this disk doesn't bound the disk in this torus. Therefore, this torus here is compressible. However, another torus is always incompressible in the outside. What is another torus? Another torus is a torus whose core is a non-trivial knot. So one example here of another torus is this one. When we consider here the core of this torus is this knot here. So we see that this knot here is non-trivial. So we have here another torus. When we have another torus, a disk like that doesn't exist here in the outside. Therefore, another torus is always incompressible in the outside. But when we look here in this side of the torus, we can find a disk like that. And this disk here, we see that its boundary doesn't bound a disk in this torus. Therefore, this torus is compressible in its inside. However, if we see that if we want to make it incompressible in the inside, we need to remove some parts of its inside. One way to do that, if we consider here, let's call here this knot K, the knot that is wrapping around the core of the torus. If we consider now this torus here in the three manifold, we see now that a disk like that doesn't exist, because now we have a puncture disk. So this torus is incompressible on the inside. Therefore, it is incompressible, because to be incompressible, it must be incompressible on the outside and the inside. So here we have an example of incompressible torus. Now let's consider K a knot and T a torus in the complement of this knot. This torus is said to be not bound parallel if it cannot be isotopic into the bound of a tubular neighborhood of this knot. So let me start here with one example that is bound parallel. So let's consider here again the core of the torus here. So K, in this case here, is going to be the core of the torus. So K is this knot here. So a tubular neighborhood of this knot, it looks like something like that. And we see that this torus here can be isotopic to the bound of a tubular neighborhood of this knot. We just shrink this knot here, just shrink it. So here we have an example of a torus that is bound parallel. However, if we consider now this torus here, where K is this knot wrapping around the core of this torus, we see now that this torus is no longer bound parallel. So here we have an example of a torus that is not bound parallel. Therefore, we define an essential torus in the complement of a knot as a torus that is incompressible, is not bound parallel. So as we discussed, here we have an example. This black torus is an essential torus for the knot that is wrapping around its core. So that's an example of an essential torus. Now we know what is an essential torus, but before defining twisted torus knots, let me talk a little bit about more torus knots. As I said, torus knot can also be defined as knots that can be embedded on the trivial torus. The trivial torus is this torus here. When a torus knot is embedded on the trivial torus, it wraps along the longitude and the meridian a certain amount of times. So a torus knot is defined by a pair of intertors, where this first number here measures the amount of time that is not wrapped along the longitude. The longitude is here. And the second number measures the amount of time that it does not wraps along the meridian. So the meridian is curved. So in this case here, we have that it does not wraps 5 times along the longitude and 2 times along the meridian. So here we have the 5-2 torus knot. Now we are ready to define twisted torus knots. Twisted torus knots was first introduced by Dean in his doctoral thesis. He was interested in studying ciphered fiber space obtained by Dennis surgeries on knots. Since then, twisted torus knots have become a rich source of research. They were discovered to have many interesting properties. So you can find many papers about them. A twisted torus knot is defined by 4 parameters: P, Q, R, and S. So this twisted torus knot with these parameters is obtained by performing a sequence of S full twists on R adjacent strands of the PQ torus knot. So to obtain the twisted torus knot, we should start here with the PQ torus knot. Then we should consider a circle encircling R adjacent strands. Then we should apply S full twists along the circle. So that's how we obtain this twisted torus knot. Torus knot are considered to be one of the simplest families of knots. As I said, each torus knot is characterized by a pair of intertors. So with this point of view, if we consider that twisted torus knot is the simplest family of knots, then we can say that twisted torus knot is the second simplest family of knots. However, as we're going to see, now we have a much more complicated families of knots. So let me give you one concrete example. On the left, we have the 5-2 torus knot, and on the right, we have a circle encircling 3 strands of this torus knot. Then to obtain the twisted torus knot, we should apply some full twist along the circle. So a full twist looks like that. We first cut that circle in 2. So now we have 2 circles. Then we apply some full twists along in one of the circles. In this case here, we applied one positive half twist. After that, we glue the circles back as illustrated in the third picture. In that picture, it looks like that. So here we have the 5, 2, 3, 1 twisted torus knot. So now we have a new family of knot to study. So the natural question is, when is this twisted torus knot a torus, a satellite, or a hyperbolic knot? So we would like to know when a torus knot is a satellite, a torus, or a hyperbolic knot based on the parameters. Many people have been interested in this question, and you can find many papers about this topic. In particular, Lee proved that a twisted torus knot with these parameters, has an essential torus in its exterior. Therefore, it is a satellite knot. After that, Morimoto classified this one here. He proved that a twisted torus knot with these parameters also has an essential torus in its exterior. Therefore, it is also a satellite knot. Therefore, here we have two infinite families of satellite twisted torus knots. Then he asked, are there twisted torus knots with essential tori which are not as in the last theorems? So here he was wondering if Lee and he had found all satellite twisted torus knots. However, I need to mention that Lee slightly generalized Morimoto's argument, and he was able to find another family of satellite twisted torus knots that can be seen as a slight generalization of Morimoto's theorem, the last theorem. However, the answer to this question has been confirmed to be no when the model of S is greater than 1, because Lee found the geometric types of them. So he proved that most of them are hyperbolic and a few are torus knots. However, this question and the geometric classification of twisted torus knots are open for when the module of S is equal to 1. However, recently we are able to show that the answer to this question is certainly yes, because we found two new different families of satellite twisted torus knots for when the module of S is equal to 1. So the first family is this one here. If we consider K positive, then a twisted torus knot like this one here with these parameters has an essential torus in its exterior. So it is a satellite knot. The next one is this one here. If we consider P and Q satisfy these conditions, then this twisted torus knot here has an essential torus in its exterior. Therefore, it is also a satellite knot. So here we have two infinitely families of satellite twisted torus knots. Also, in the literature of twisted torus knots, was believed that if we had a twisted torus knot here with these parameters, P, Q, 2, and S, where this number here is 2, is like here, was believed that a twisted torus knot with these parameters didn't contain no closed essential surfaces in its exterior. But the theorem here proves that they exist. So that's the reason behind the title, unexpected essential surfaces among exterior of twisted torus knots. So today, because of the timing, I'm going to sketch just the proof of the second theorem. However, you can find both proof on archive. You can use the same title. Also, the proof that I'm going to sketch today is different from the one that you can find on archive. We found this different idea when we study a different case, but I think this idea here is going to be easier to explain. Before starting to sketch the proof, let me tell you what is a braid. A braid is a set of parallel strands with over and under crosses between them, as illustrated here in this figure, where on the left we have the trivial braid, because now 8 strands, there is no crosses between 8 strands. On the rightmost figure, we have a non-trivial braid, because now we can see that there are strands, there are crosses between 8 strands. A braid is not a knot. However, we can obtain a knot from a braid. by closure in the braid. To obtain the closure of a braid, we should connect the first strand in the top to the first strand in the bottom, the second strand in the top to the second strand in the bottom, and so on, as illustrated here by this figure, where here we have the closure of this braid here. So that's how we can obtain a knot from a braid. Let's denote by sigma I the overcrossing between the I and I plus 1 strand, as illustrated here in this figure. These crossings, they generate the braid group. It means that every braid can be represented as a sequence of crosses like this one here, or its inverse. So here, let me give you one concrete example. Let's write here this braid using the generators of the braid group. The first thing that we notice here is that this braid is a positive braid because all of its crossing has this form here. So when we have a braid that all of its crossings of one type, is it called a positive braid. So we start here with this crossing here. This crossing is sigma 1. So we have sigma 1. This crossing here, we see that it is sigma 2. Then here we have sigma 3, sigma 4. So sigma 3, sigma 4. Then this line here, we see that it's similar to the first one. So here we put 2. The third horizontal line, we have sigma 1, sigma 2. So we have sigma 1, sigma 2. This line here, we see that it's similar to this one here. So here we put sigma 3. So we have written this braid using the generators of the braid group. And we see that the closure of this braid here is this twisted torus knot here. 5, 2, 3, 1. More generally, we can say that if we have a twisted torus knot here with these parameters, P, Q, R, S, where R is less than P, and S is positive, is this closure here of this braid. P minus 1, Q1 until Q R minus 1 R S. So the closure here of this braid is this twisted torus knot. So let me give you now another example. Here now we have a negative braid because in the top we have crossings, as in the other case, positive crossings. And in the bottom here, we have negative crossings which has this form here. So when a braid has crossings of two types, is it called a negative braid. So let's write again this braid here using the generators of the braid group. We see that the top, the first two horizontal lines, is similar to the previous case. So we have here as before, sigma 1, sigma 2, sigma 3, sigma 4, 2. Then let's consider here this line. This line starts here. So we know that this crossing here is sigma 2. But this crossing here looks like more that. So if this one here is sigma 2, this one here should be sigma 2 minus 1. Sigma 2 minus 1. So we put here sigma 2 minus 1. Then this one here with a similar argument, this one here should be sigma 1 minus 1. This line here is similar to this line here. So here we put 3. So here we have written this braid using the generators of the braid group. Also, we see that the closure of this braid here is this twisted torus knot here. 5, 2, 3, minus 1. 5, 2, 3 minus 1. More generally, we can say that if we have a twisted torsion knot here, P, Q, R, S, where R is less than P and S is negative, is this closure here of this braid P minus 1, Q. Then here we have R minus 1 until sigma 1 minus 1 RS. So the closure of this braid here is this twisted torsion knot. Now, let's consider R until Rn, they are all greater than 1. And let's consider Si all positive. So, a K-link with these parameters is defined to be the closure of this braid here. To obtain this braid, we should start with the biggest parameters, which are R1, S1 in the top. Then we should consider the second biggest parameters, which are R2, S2. Then we place in the bottom the smallest parameters, which are Rn, Sn. So that's how this braid here looks like. And the closure of this braid here is this K knot here. So that's how a Dremel K-link looks like. Now we have here this lemma. So let's consider P, Q, K, A, and B satisfy these conditions. Then this lemma here states that this twisted torsion knot here is equivalent to this K knot here. I'm going to sketch the proof of this lemma using one concrete example. So we're going to work with this twisted torsion knot here, 12, 5, 11, minus 1. So in this case here, P is 12, Q is 5. Therefore, this first equation here, this equation here is 12 minus 1 minus 2, 5 minus 1, which is 2. It's implied that K is 2. Then this equation here is 12 minus 2, which is 10. So we know K is 2, so K multiplied by A, it's implied that A is 5. And finally, the last equation here, we have 5 minus 1, which is 4. So 2B, it's implied that B is 2. So we know K, A, and B. Therefore, we know the parameters here of this K knot. So it should be 11, 2, 10, 1, 9, 1, until 7, 1, 4, 1, 3, 1, and 2, 1. So we need to prove that this twisted torsion knot here with these parameters is equivalent to this K knot here with these parameters. So we start with this twisted torsion knot on the left with the standard projection. So let me Sorry. So we start here with on the left. Then the first thing that we do is we consider here this line, this strand here of this knot. The first thing that we do, we push the strand completely to the left. We push it in this direction here. We can do this isotopy. We push it to the left, then we obtain here the second braid. Then we do the same thing for the third and the second and the first horizontal lines. So we push them all to the left. We push them all to the left. After that, we're going to end up here with this braid here. So we have pushed pushed it all to the left. Now we have this braid here. We know in the blade closure, this point here is connected with this point here, as illustrated here by this figure. So in the blade closure here, we have this strand. We see that we can remove this strand without changing the knot. We just shrink it. Technically, is it called the second Markov move? But the idea is kind of like that, just shrink. After that, we obtain here this braid. Then we see that this strand here has some crossings along it, but we can remove all of them by pushing it to the left. So we push the strand to the left. After that, we end up here with this braid. This braid here has now some positive crosses in the top and some negative crosses in the bottom. When positive and negative crosses they meet each other, they can be canceled. So when we have a picture like that, it's equal to like that. So the next thing is that we're going to do, we're going to push the positive crossings here in the top to the bottom to be canceled with some negative crosses in the bottom. We start here with the first crossing. This crossing here, we push it along the blade closure to be canceled with this crossing here. So we obtain this braid. Then we do the same thing for the other crosses in the top. So after doing for all of them, this part here is going to be gone and some parts here of the bottom as well. So after doing that for crosses in the top, we obtained here this braid. We obtained the first braid here. The first braid. Sorry, this braid here, the braid on the left. Now the next thing that we do, we push here this part down. We push it down. Then after that, we obtain here this braid. The third braid now can be obtained from the second one by flipping it horizontally. So we flip here this braid horizontally to obtain here this braid. And now we see that this braid represents a K knot. We can see that the closure of this braid is a K knot. Let's calculate the parameters of this K knot here. So we see that this braid here has 11 strands, and there are 2 horizontal lines with 11 strands. So we have that the first parameters of this K knot here is 11, 2. Then here we have 10 until 7. So it is 10, 1 until 7, 1. Then here we have from 4 to 2. So it is for 1, 3, 1, 2, 1. So we obtained exactly the key note that we wanted. And the general idea to prove the general statement of the lemma can be taken from this specific case. Now, let me define half twists. So let's consider now we have a circle encircling some strands of a knot. Then we cut the circle in two. So now we have two circles. Then we apply a half twist in one of the circles. A half twist means that we rotate one of the circles by a rotation of 180 degrees, like that. After that, we glue the circles back. So that's how a half twist is obtained. If you rotate that circle by a rotation of positive 180 degrees, is it called a positive half twist? On the other hand, if we rotate that circle by a rotation of negative 180 degrees, is it called a negative half twist? We see that half twist is defined quite similar to full twists, but instead of applying full twist, we apply half twist. Also, we see that two full twists in the same direction gives us a full twist. So let me give you some examples. So we start here. This one here is a positive half twist on 5 strands. And here we have a negative half twist on 5 strands. So here we have positive and here we have a negative. More generally, we obtain here this braid if we apply a positive half twist on k strands. And we obtain this braid if we apply a negative half twist on k strands. So we can see that half twist is kind of half of a full twist. Now let me define here this link here. So let's consider PQK, A and B satisfying these conditions. So this link here is a link with 4 components. The first one is the P minus 1K toys link. Then J1 is a circling KA strands of the toys link. J2 is a circling K times 1 plus B strands of the toys link. And finally, J3 is a circle encircling K, B strands of the toys link. So that's how the toys link looks like. Is it formed by a toys link together with some circles. Now, this lemma here, let's first consider P, Q, K, A, and B, satisfying these conditions. Then, this lemma states that this K knot here, again, that K knot that we associate to a twisted torus knot can be obtained from this link here after doing one positive half twist. After doing one positive half twist on J1, one negative half twist on J2, then one positive half twist on J3, followed by gluing trivial solid tori along the J1, J2, J3 to remove them from the diagram. So let's try to see what is happening with that example. So this K knot here, again, this K knot here, K knot that we associate to this twisted torus knot here, 5, 11, -1. So in this case here, we discover that K is 2, A is 5, and B is 2. So here they circle encircling KA strands, which is 10. This one here is encircling K times 1 plus B, which is 6. And this one here is encircling KB strands, which is 4. And at the top here, we should have the P minus 1 K torus link, which is 11, because P here is 12, so 11, 2. And that's exactly what we have. Then we should apply here a positive half twist here along the circle, followed by a negative half twist here along the circle, and finally a positive half twist here along the circle. The positive half twist here along the red circle gives us this braid. The negative half twist along the blue circle gives us this braid. And finally, the positive half twist along the green circle gives us this braid. Then after that, to remove these circles from the diagram, we glue solid tori along them. So that's why we cannot see these circles more in this diagram here in the second. However, we see that the negative half twist along the blue circle is cancelled with some parts of the positive half twist along the red circle. To see that, we start here with this strand. There are some crossings along this strand. However, we can remove them all by pushing it to the left. So we push the strand to the left to remove the crossings along the strand. Then we can do the same thing here for this strand, this strand, this strand, this strand, and so on. So after that, all of this part here is going to be gone. So we obtained here the third braid. And we see that this braid here represents this K knot. So that's how we can obtain here this K knot from this link here by applying half twists. Now this lemma here states that, again, let's consider P, Q, K, and B satisfying these conditions. Then this lemma here stated that this K knot here has an essential torus in its exterior. So it is a satellite knot. Again, this K knot here is that K knot that we associate to a twisted torus knot. So let's try to see what is happening for that example. When we apply some half twist along these circles, we're going to obtain that K knot that we associated to this twisted torus knot here. The first thing that we're going to do, we're going to construct an essential torus for this link here. The first thing that we do is we remove here one strand of this braid. This braid has 11 strands. We're going to remove the rightmost strand, the blue strand here. To do that, we see that this blue strand can be pushed down and shrink. So after that, this blue strand here is going to be a little strand here. So now we have a braid on 10 strands. Now let's consider here a tube. We start with a tube here in the top, a tube like that. Then we push this tube following the black. There are two horizontal lines here in this braid. This braid here is encircling 10 strands, and this one here is encircling 6, and this one here 4. So it means that all of them are encircling a multiple of 2 strands. And again, this braid here has 10 strands. It means that after pushing this tube here in this direction, following the black knot, we're going to end up with a tube here in the top. We end up with a tube here in the top. Then we glue them to obtain the torus. So we glue them to obtain a torus. So we're going to obtain here this purple torus here. After that, we now have this purple torus. And we see that this purple torus, so it is essential because it is incompressible and not bounded parallel in either sides. So we have constructed an essential torus here for this link. However, we want an essential torus for that K knot. That K knot is obtained again by a positive half twist here along the circle, followed by a negative half twist here along the circle, and finally a positive half twist here along the circle. However, we see that this torus is not going to be break after this procedure because these circles don't puncture this torus. So after doing all of this half twist, we're going to obtain that K knot that we wanted and a new torus. So we have here that K knot and we have a torus in the complement of this K knot. So we see that this torus is essential because it's knotted, and we see that kind of the K knot is wrapping kind of 2 times along its core. So here we have an essential torus for this K knot. And the general idea can be taken here to prove the general statement of the lemma can be taken here from this explicit case. Therefore, we have sketched the proof of here of this lemma. So it states that if we consider PQ satisfying these conditions, then this twisted torus knot here has an essential torus in its exterior. The first thing that we did, we proved that this twisted torus knot here is equivalent here to this K knot. Then we proved that this K knot here is a satellite knot. It means that its complement has an essential torus. Therefore, this one here also has an essential torus. So that's the sketch of the proof. That's the sketch of the proof of the theorem. So thank you very much, everybody, for your attention. Feel free to ask any question if you have. Thank you very much.
All right.